In the year 2050, a message arrives on Earth from a place no human eye has ever seen up close. Not from Mars, not from Jupiter, not from the icy moons of Saturn, from another star. The message is tiny, just a narrow beam of data, so weak that an ordinary phone would never even notice it. But on Earth, entire observatories are waiting for it. Radio dishes turn toward the southern sky, quantum clocks synchronize, supercomputers wake up, and inside a sealed room, a group of scientists watches the first pixels appear on a screen. At first, it looks like nothing. A red star, a dark curve, a faint blue-gray crescent. Then the image sharpens. Clouds, not dust, not noise, clouds. And beneath them, a surface that should not be visible from Earth at all. A world circling the nearest star to the Sun. A world that for decades had been only numbers in a database. Mass, orbit, estimated temperature, probability of liquid water. But now it is no longer a probability, it is a place. And then the chemical data arrives. Methane, carbon dioxide, water vapor. A strange imbalance in the atmosphere. A pattern that should not last for long unless something is constantly renewing it. And in that moment, the room goes completely silent. Because if those readings are real, humanity has not just found another planet. Humanity has found a second living world. And the most disturbing part is this. The mission was never designed just to look at it. It was designed to prepare the first human expansion beyond the solar system. That sounds insane. It sounds like science fiction wearing a lab coat. But if you follow the actual technology being developed right now, the plan begins to look much less impossible and much more unsettling. Because the first colony on another living planet will probably not begin with astronauts stepping out of a shiny spacecraft. There will be no flag, no speech, no heroic footprint in alien dust. The first colonists will be machines, smaller than insects. And they may arrive before we have even decided whether we are allowed to be there. To understand how we get to that terrifying point, we have to start with a planet that changed everything. A planet that is not actually close enough to colonize by 2050, but became the reason humanity started trying. K2-18b, a world more than 100 light-years away, orbiting a small red star in the constellation Leo. It is not Earth. It is larger, heavier, stranger. Some scientists call it a possible Hycean world, a planet with a hydrogen-rich atmosphere and perhaps a global ocean underneath. When the James Webb Space Telescope studied its atmosphere, it found carbon-bearing molecules, methane, carbon dioxide, the kind of chemistry that makes astrobiologists sit up a little straighter. And then came the molecule that made the internet lose its mind, dimethyl sulfide. On Earth, dimethyl sulfide is mostly produced by life in the oceans. Tiny organisms, marine plankton, living chemistry breathing into the sky. So when researchers saw a possible signal of something like it around K2-18b, the story exploded. For a few days, it felt like humanity had heard a whisper from another ocean. But here is the part that gets lost in the hype. Scientists did not confirm alien life. They found a possible clue, a controversial clue, a clue that could be real, or could be an instrument effect, or could be another molecule pretending to be the one everyone wants to see. And honestly, that makes the story even better, because this is how the search for life probably begins. Not with a spaceship landing beside an alien tree, not with a creature waving from another world, but with a tiny wobble in a spectrum, a chemical shadow, a molecule that may or may not be telling the truth. K2-18b became the spark. It showed humanity that the first sign of life outside the solar system might not come from a rocky twin of Earth. It might come from a strange ocean world wrapped in hydrogen, orbiting a red dwarf star, far beyond anything we can reach. And once that possibility entered the human imagination, one question became unavoidable. If we ever find signs of life on a world close enough to reach, what do we do next? Do we just look at it forever? Do we send a probe? Do we send machines? Do we build a colony in orbit? Do we land? Or do we stay away? That is where the real story begins. The first brutal truth is this. K2-18b is not the planet humans are going to reach by 2050. It is too far away. About 120 light-years. Even a spacecraft moving at 10% the speed of light would need more than 1,000 years to get there. A normal spacecraft would need millions. So if someone tells you that astronauts are packing bags for K2-18b, Congratulations, you have found either a liar or a YouTube thumbnail artist. But K218b matters because it gives us the blueprint. It tells us what to search for. It tells us what gases to look for. It tells us what kind of planet might hide an ocean. And most importantly, it tells us that the first living world we discover may be deeply weird. Not blue skies and forests, not beaches and birds. Maybe a massive ocean under a crushing hydrogen atmosphere. Maybe an endless warm sea beneath clouds hundreds of kilometers thick. Maybe life that never sees stars. Maybe organisms drifting through an alien ocean, producing gases that leak into the sky and travel across space as spectral fingerprints. That is the first stage of colonization. Not rockets, not bases, not humans. Selection. Humanity has to choose the target, and by 2050, the target cannot be simply the most exciting planet. It has to be the nearest planet with the strongest evidence of life, the best chance of liquid water, and the lowest chance of killing every probe we send. The obvious candidate is not K218b, it is Proxima Centauri b. Proxima b orbits the closest star to the Sun. It is only a little over 4 light-years away. In cosmic terms, that is our next-door neighbor. In human terms, it is still a nightmare. A beam of light takes more than 4 years to cross that distance. A radio message takes more than 4 years to get there, and more than 4 years to come back. If you ask a question, the answer arrives nearly 9 years later. That alone is enough to make the idea of colonization feel absurd. But Proxima b has one thing K218b does not have: reachability. It is a rocky super-Earth candidate in the habitable zone of a red dwarf star. It may be tidally locked, meaning one side could face permanent day while the other is frozen in permanent night. Its star is violent. Red dwarfs can flare. They can blast planets with radiation. They can strip atmospheres away. So Proxima b may be a dead rock. Or it may be exactly the kind of place where life survives in the narrow border between light and darkness. Imagine a planet where the sun never rises or sets. A permanent red star hanging in the same place forever. One hemisphere scorched, one hemisphere frozen, and between them, a ring of twilight, where winds scream from the hot side to the cold side, and the sky glows the color of old blood. If life exists there, it would not look like Earth life in a nature documentary. It would be life adapted to extremes. Life under rock, life under ice, life in dark oceans, life clinging to a twilight band like a civilization clinging to the edge of a knife. And that is why Proxima b is the terrifyingly logical target. Not because we know it is alive, we do not, but because if future telescopes detect a real atmospheric imbalance there, humanity will suddenly face a question it has never had to answer. What is the protocol for approaching a living planet? Because make no mistake, if by the 2030s or 2040s, the next generation of telescopes finds oxygen, methane, water vapor, or other suspicious chemistry around a nearby rocky world, the race begins immediately. Every space agency, every billionaire, every defense contractor, every university, every nation that does not want to be left behind. They will all understand the same thing. The first civilization to reach another living world does not just win a scientific prize. It gets to write the rules of interstellar history. And that is where things get dangerous. Because the technology that could reach Proxima b already has a name: Breakthrough Starshot. The idea is almost offensively simple. Do not build a giant spaceship. Do not carry fuel. Do not carry astronauts. Do not even try to slow down. Instead, build a spacecraft so small that it weighs only grams. Attach it to an ultra-thin reflective sail. Then hit that sail with an enormous laser array on Earth or in orbit, pushing it faster and faster until it reaches a significant fraction of the speed of light. Not thousands of kilometers per hour, not millions, hundreds of millions. At that speed, the trip to the Alpha Centauri system could take about 20 years. 20 years. That means a probe launched in the early 2030s could reach the nearest star around 2050. And yes, that sentence should make your brain do a small system reboot. But Starshot is not a normal mission. A normal spacecraft is like sending a submarine across an ocean. Starshot is like firing a snowflake from a cannon and hoping it survives a hurricane, crosses another solar system, takes pictures while moving at absurd speed, and then whispers the results back to Earth with the energy budget of a flashlight. It is ridiculous, and that is why it might work. Big ships are slow because they are heavy. Heavy things need fuel. Fuel adds weight. More weight needs more fuel. The rocket equation is basically the universe laughing at our ambition. So Starshot cheats. It removes almost everything. The probe becomes a chip, a wafer, a flying piece of technology with sensors, a camera, a power source, navigation, and a communication system packed into something smaller than a credit card. The sail becomes a mirror thinner than a human hair. The engine stays at home. That is the strange genius of the plan. The most powerful part of the spacecraft is not on the spacecraft. It is the laser system pushing it from far away. For a few minutes, Earth turns into a cannon. The lasers fire. The sail catches the light. The probe accelerates harder than any spacecraft ever built. And then, it is gone. No engine burn, no steering wheel, no second chance. Just a tiny machine screaming into the dark between stars. Now imagine not one probe, but thousands. A swarm. Because most of them will fail. Some will be destroyed by dust grains in interstellar space. At a significant fraction of light speed, even a microscopic particle becomes a bullet. Some probes will lose alignment. Some will malfunction. Some will arrive at the wrong angle. Some will simply vanish forever, becoming invisible artificial meteors drifting between stars. But if even a handful survive, they could do something no human-made object has ever done. They could fly past another star. They could image its planets from close range. They could smell atmospheres with tiny spectrometers. They could measure magnetic fields, radiation, cloud patterns, surface reflectivity, and perhaps the chemical scars of life. This is not colonization yet. This is reconnaissance. But every colony in history begins the same way. First, someone maps the coast. And in this case, the coast is 4 light years away. Here is where the 2050 scenario becomes frighteningly plausible. By the late 2020s and 2030s, Earth builds better telescopes, giant ground-based observatories, space telescopes designed specifically to block starlight and see faint planets. Maybe interferometers spread across space, combining their vision like one enormous artificial eye. They begin watching Proxima b and other nearby planets night after night, year after year. At first, the data is messy. Then patterns appear, thermal maps, seasonal changes, maybe clouds, maybe signs of an atmosphere, maybe a chemical disequilibrium that refuses to go away. Oxygen and methane together would be suspicious. Water vapor would be interesting. Certain sulfur compounds would be electrifying. No single molecule would prove life, but a combination of gases in the right temperature range, on the right planet, with the right stability over time, would become very hard to ignore. And then the world changes. Not with a press conference that says, "Aliens confirmed." Science almost never works like that. It changes with a sentence like this: "The observed atmospheric composition is difficult to explain without biological activity." That is the sentence that would quietly break civilization, because it would mean we are no longer searching for life in the abstract. We are looking at a specific address, a planet, a star, coordinates, a place where biology may already be happening. And from that moment on, every delay becomes political. Should we launch the probes now? Should we wait for better instruments? Should one nation control the mission? Should private companies be allowed to send their own probes? Should the United Nations create an interstellar law before anyone touches that system? And the darkest question of all, if there is life there, do we have the right to colonize it? This is the part people usually skip because it ruins the adventure. but it is the most important part of the story. Colonizing a dead world is one thing. If Mars has hidden microbial life underground, that already creates huge ethical problems. Now multiply that by a whole planet. A living exoplanet is not free real estate. It is a second Genesis. If life evolved there independently, it might be the most valuable discovery in human history. More valuable than gold, more valuable than oil, more valuable than any nation, company, or empire. Because it would answer a question older than science. Is Earth special? And if the answer is no, then the universe is not silent because life is rare. The universe is silent because distance is cruel. So how do you colonize a world you may not even be allowed to touch? You begin without landing. That sounds strange, but the first colony near a living exoplanet would probably be orbital, robotic, and extremely cautious. A Starshot-style flyby probe cannot stop. It would blast through the system at insane speed, collecting data for minutes or hours, then continue into the dark forever. But its data could tell us where to send the next wave. The second wave would be smarter, not necessarily bigger at first. Bigger is still hard, but more specialized. Some probes would be cameras, some would be atmospheric sniffers, some would be dust collectors, some would be magnetic field mappers, some would be designed to deploy tiny reflectors or communication nodes. Some might aim not at the planet, but at asteroids, moons, or stable orbital points nearby. Because if the planet is alive, the safest place for the first colony is not the surface. It is the neighborhood. Think of it like building a research station outside a protected forest. You do not start by driving bulldozers through the trees. You place sensors around the edge. You watch. You measure. You learn what lives there before your own contamination destroys the evidence. Except in this case, the forest is an entire world, and your bulldozer is the first human mistake to cross interstellar space. By 2050, the first realistic colony would not look like a city. It would look like a network, a robotic listening post around another star. Tiny probes scattered through the system, using the star itself as a power source and possibly as a gravitational lens. Small machines using light, dust, plasma, and radiation to orient themselves. Autonomous software deciding what to observe, because every command from Earth takes years to arrive. That last part matters. You cannot joystick a robot from Earth when the delay is 4 years one way. There is no mission control saying, "Turn left." There is no emergency button. There is no engineer staying late to fix the rover before sunrise. The probes have to think, not like humans, not emotionally, not consciously probably, but they need enough onboard intelligence to make decisions alone. If a dust storm forms, watch it. If a chemical plume appears, follow it. If the star flares, protect the instruments. If something moves in a way that cannot be explained by wind or geology, keep recording. Imagine the first alien wildlife footage being captured by a machine that cannot understand what it is seeing. A pattern in an ocean, a dark bloom under clouds, a night-side glow, a seasonal color shift across the twilight zone. The probe sends the data home. 4 years later, Earth receives it. And maybe 20,000 scientists start arguing immediately. Is it life? Is it chemistry? Is it geology? Is it instrument noise? Is it our own contamination? That last one is the nightmare, because even a tiny probe carries risk. Earth microbes are stubborn little monsters. They survive cold, radiation, vacuum, salt, heat, and almost everything else we throw at them. Space agencies already sterilize missions that might touch places like Mars or Europa, but interstellar missions would require something far more severe. A living exoplanet would need planetary protection on a level humanity has never attempted. Every screw, every sensor, every material, every molecule. Because if you send Earth biology to another biosphere, you may never be able to tell what was native and what came from us. That is how you ruin the greatest scientific discovery in history. Not with war, not with greed, with bad cleaning. Which is embarrassingly human, honestly. But suppose we solve that. Suppose the probes are sterile. Suppose they arrive. Suppose they confirm that the planet has an ocean, an atmosphere, and a strong biological signature. Then the mission changes. Humanity stops asking, "Is anyone out there?" and starts asking, "How close can we get without becoming the disaster?" That is when the first true colony begins. Not on the planet, around it. Robotic platforms in orbit. Autonomous factories built from local asteroids. Mirror arrays for communication. Telescopes the size of cities, assembled by machines in deep space. Long-term monitoring stations that can watch the planet for centuries without landing. This sounds less dramatic than astronauts walking on alien soil, but it may be far more powerful. Because the first interstellar colony might not be a human settlement at all. It might be a scientific machine civilization, built by us, operating without us, waiting in orbit above another living world. Now let's imagine the full timeline. Not the fantasy version where a giant silver ship leaves Earth tomorrow and lands on an alien beach by Thursday. The version that could actually unfold. First, the telescope era. From now through the 2030s, humanity keeps staring at nearby planets. K218b remains the emotional trigger, the planet that taught the public to care about atmospheric biosignatures. But the real hunt moves closer, toward Proxima b, TRAPPIST-1, and other small worlds around nearby red stars. The goal is chemistry. We are looking for atmospheres that do not make sense. Life eats, breathes, reacts, and changes its environment. Oxygen should react away. Methane should break down. Certain gases should not sit together peacefully for long periods. When they do, something is replacing them. Maybe volcanoes, maybe oceans, maybe sunlight-driven chemistry, maybe life. Then comes the decision. Once a nearby world becomes suspicious enough, governments and private groups begin funding the interstellar swarm. Publicly, they will call the probes scouts. Quietly, everyone will know what they are really doing. They are choosing the first place where humanity may touch another biosphere. Then comes launch. A laser array fires at thousands of light sails. One by one, the tiny probes accelerate into interstellar space. For a short time, they are the fastest human-made objects ever created. Then, they disappear. Years pass. The public gets distracted. New scandals happen. New wars almost happen. People argue about money, climate, AI, borders, everything humans always argue about. Meanwhile, the probes keep going. Silent, cold, almost weightless, moving through interstellar darkness toward a red star no human has ever visited. Around 2050, the first survivors cross the target system. They do not stop. They cannot stop. At those speeds, a planet is not a destination. It is a bullet-time encounter. They turn their cameras, they scan the atmosphere, they measure dust, radiation, magnetism, clouds, and heat. They look for oceans, they look for chemistry, they look for the fingerprints of biology. Then they transmit. And Earth waits. Because even after arrival, the data still needs years to cross the distance home. The event may happen in 2050, but humanity may not fully see it until 2054 or 2055. And if those first images show a living atmosphere, a possible ocean, or a biosphere that refuses to be explained away, humanity changes forever. Not because we have landed, because we now have an address. The next phase is the robotic beachhead. A second generation of missions launches with better targeting. Maybe magnetic sails to slow down. Maybe laser braking. Maybe probes that can use local dust, asteroids, and sunlight. Maybe most of them fail because the universe is rude and engineering is pain. But eventually, one machine stays. That is the key word. Stays. A flyby visits. A colony remains. The first object that enters another star system and continues operating there for years will be the real beginning of colonization. Not because it owns anything, not because it plants a flag, because it makes humanity present. A few kilograms of machinery around another star may not sound like an empire, but it would mean the solar system is no longer the only place where human technology lives. This is where robotic builders become important. They do not build cities first. they build survival. 3D printers melt local minerals. Tiny factories make replacement parts. Solar collectors unfold. Communication lasers point back toward the sun. A base begins to grow without a single human voice inside it. And then comes the hardest question. Do we land? If the target world is dead, the answer is still difficult but simpler. If it is alive, everything changes. A living exoplanet is not empty space. It is not free land. It is not a reward for building faster machines. It is a second beginning. If life evolved there independently, then touching that world would be like touching a second version of creation. Every microbe, every ocean current, every strange molecule could contain an answer to the deepest question we have ever asked. Is Earth special? And if the answer is no, then the galaxy is not a graveyard, it is a wilderness. That means the first act of interstellar colonization may have to be restraint. Maybe we do not land. Maybe we build in orbit. Maybe the first human presence around another living world is a sanctuary station, a ring of machines and habitats watching from above, close enough to learn, but far enough not to contaminate. Imagine being born in a habitat around Proxima Centauri, seeing a living alien planet below you every day, and knowing you are not allowed to go down. Beautiful, maddening, probably necessary. Because the real test may not be whether humanity can reach another living planet. The real test may be whether we can reach it and choose not to ruin it. So when people ask, will humanity colonize the nearest exoplanet with signs of life by 2050? The honest answer is complicated. Humans will not be walking there by 2050. But humanity may begin the process. We may identify the first real target. We may launch the first interstellar swarm. We may receive the first close-up data from another potentially habitable world. We may establish the first machine presence around another star. And we may be forced to create laws for a place no human has ever touched. That is bigger than a landing. A landing is a moment. A colonization program is a civilization changing direction. By 2050, the question may no longer be, are we alone? It may be something much harder. What kind of species do we become when we discover we are not? Do we become conquerors? Curators? Gardeners? Invaders? Protectors? Children with dangerous toys? The answer will not come from the planet. It will come from us. Because space is not just a place we explore. Space is a mirror. Every time we look deeper into it, we learn something uncomfortable about ourselves. K2-18b did not give humanity proof. It gave us a maybe, a possible ocean, a possible biosignature, a possible second beginning. And maybe is powerful. But maybe is also dangerous. Because if you want something badly enough, you can mistake a hint for proof. You can mistake a target for destiny. You can mistake discovery for permission. So the first mission to a living exoplanet will have to carry more than cameras and sensors. It will have to carry discipline. The discipline to doubt exciting data. The discipline to protect what we do not understand. The discipline to admit that reaching a world does not mean owning it. And if we can do that, then 2050 may be remembered not as the year humans colonized an exoplanet, but as the year humanity became mature enough to begin. A tiny signal from another star, a few pixels on a screen, a chemistry pattern in an alien sky, a machine whispering back across 4 years of darkness. That may be how the next chapter starts. Not with a roar, not with a landing, not with a flag, with a question. There is life there. Now what? If you enjoyed this journey, hit the like button, subscribe, and tell us in the comments what humanity should do if we confirm life on another planet. Should we go there? Or should we protect it from us? Because the answer may define the future of our species. And maybe, just maybe, something out there is already waiting to see what we choose.